Welcome to MOOC course on Introduction to Proteogenomics. In today's lecture, Dr. David Fenio will talk about association and marker selection. Marker selection helps to model an easy interpretation taking few features into account. Most of the protein candidates may not directly relate to the phenotype, so marker associated selection or mass help us to feature those candidates and build a good predictive model. Dr. Fenio will also discuss about how many features need to be considered for building reliable model and why multiple features makes a model complex. What is the optimal number of features? He will briefly discuss different kinds of methods which are available which could help in the feature selection. He will also highlight what is data snooping. So, let us welcome Dr. David Fenio for his last lecture.
The other thing is marker selection that we already mentioned earlier. So now we do all these measurements and we know that most of the proteins or most of the transcripts are not going to be related to our phenotype. So it would be much better to just have build the model using the ones that we know are related, but of course we don't know which ones to start with. So we need to. So if we look at markers, so why do we do marker selection? So having few features, it makes the model easier to interpret. So one thing that we've talked about building these predictive models. And we want to predict something, but if we can also understand, that's of course a much better thing. And often when we build very complex models, we don't understand and maybe won't have a chance to understand. Few features, so it's easier to interpret. We can start thinking about biological function. They're also less likely to overfit because fewer parameters. But usually we get a little bit lower prediction accuracy. So that's something to balance, and that's what we use to then decide how many features. So as opposed to if we have many features, it's difficult to interpret, we don't know what's going on, and then of course more likely to overfit because we do have an enormous amount of parameters. But of course as we add in more and more things, we get higher prediction accuracy, but we're not sure whether that's really real. So there are a few different ways to do this. One set of methods are called filtering methods. So in these we look at what is the predictive power of each protein. And then, of course, and then we select the ones with the highest predictive power. And so we look for which proteins have high correlation with the target variable. So whatever we, let's say, tumor subtype. We also don't want a lot of predictors that are correlated with each other. We want them to be somewhat uncorrelated, and also we want them to have lots of information, and that's pretty much the same as high correlation with the target value. So, but this is now we evaluate each individually. Now, the other class is these wrapper methods where we look at the predictive power jointly, and so the idea is that they're not independent of each other. So probably we will get a better result using where we evaluate them jointly. So there are two ways. So one is that we start with let's say the one that has most information, then we add the second one, we evaluate them together, and then what we mean by evaluating is we check, is there any additional point of adding the second one? Does it improve our results? And then we continue adding until it's not, the results don't improve anymore. And of course, this, again, we have to do this within cross-validation, because otherwise it will overfit. Then that was forward selection. Backward selection is that we remove instead. And then we can also, there are, people have combined this. So one very popular way of doing this is called recursive feature extraction, which is probably the most widely used one. Some methods like lasso. So lasso was when we regularized adding in the absolute value of the parameter vector times a constant. There we actually get explicitly feature extraction, and some variables will fall out. Some parameters will become zero. So then with marker selection, so the question is, what's the optimal number of features? So that's usually we want two things. We want it to be as simple as possible so we can interpret it, and but we want to get good predictions still. So one thing that people talk about is the curse of dimensionality, which we definitely have always, is that we measure few samples. Even, within CPTech we measure 100 samples, that's still quite few. But for each sample we measure tens of thousands of, 10,000 proteins, maybe 30,000 transcripts, and so another 30,000 phosphorylation sites. So we have much more measurements on each variable than we have samples. And this makes things very hard, first of all, not to overfit, but also often when we find signatures, they are not unique, but we have a large, there are many signatures that are equally, would make equally good predictive models. Okay, so now finally, cross-validation. So we have all these hyperparameters that we need to decide on, but what we say, we do have our data set that we divide into train and test, but we need to decide on these variables, and we're not allowed to use the test set to decide on the hyperparameters. So what we do is we further divide the training set, but we divide it many times. So here we have taken the blue region of the training set as the training, that we actually do the training, and then we use this yellow as validation. For validation, meaning that we define, for example, the learning rate, the regularization rate, and so on. And then we do this many times for different subsets. So, for example, 5-fold cross-validation or 10-fold cross-validation are commonly used. And we can even, since we do have limited data sets, we often also do that we do another, don't do this division of training and test, but do what's called nested cross-validation. So we do a cross-validation down here, but then we do a similar cross-validation up here on top of it. So that's, and this is very important to do well. But a lot of the software packages do have this built in. Okay, so another few things I wanted to just mention. I'll only take a few more minutes. So one is sampling bias. So we really, the machine learning method will only give us what we train it for. So this is a classical example of in this election, Truman won, but the polls, the polling companies, the way they did the polls is that they called people on their home phone. And I forget, this was in the late 40s, so only rich people had phones. And they preferably, mostly voted Republican, and so the polls got it completely wrong. So here is a newspaper that actually printed it in advance because they were so sure that Truman would lose. And this is something that happens to us a lot in biomarker discovery. And so this, you'll have the slides. So it's definitely worth reading. So David Ransov has written several papers on this problem, and here this is just some list of what can go wrong. But it's definitely, one should spend quite a lot of time thinking about what, for example, if one would develop a blood test for early discovery, one shouldn't collect the normal samples in a different clinic than for the samples from people with, that have cancer. It should be, but there's a lot of, it's worth reading these and a lot of things to think about. Okay, so then again, I've said this several times, so the test set data has to be independent. Otherwise, it's not, if you train, if you test your model on something you've trained with, it's really not going to tell you how good the model is. So we talked about a little bit about when we have very complex models, it's difficult to know when, if the model tells us something about reality. So one thing, especially with images, it's easy to, so here we have an image, and I think the neural network in this case was able to say that it found that there's an electrical guitar, it thought, from this, acoustic guitar from that, and Labrador from that. So that sounds pretty reasonable. But often we can have this case where this was classified as a wolf, but what was used for classification was the background snow. And this can easily happen in proteogenomics. Since we have so much, if we build a very complex model, we can get something that's irrelevant. What happened probably was in the training set, all the wolves had snow in the background. And that's something that can happen. So another thing that is still with image analysis, with all its success, here we have an original image, 3 images, that were classified like you would you see it. But then if you add a little bit of perturbation, you can barely see any difference. Then all these 3 images are classified as ostriches. And so there is a lot, especially with complex deep learning methods, there are a lot of things that we don't understand. And it's actually even worse, these are quite complex images, but even for simple handwritten digits. So these are classified correctly. So this is the handwritten image, and below is what the neural network says. But again, if we add a little bit of noise, you see that it barely, definitely doesn't disturb us. we can still see clearly what it is. And then, for example, this 9 here becomes, according to the network, becomes a 3. And this is now people that developed this network classification knew about this problem and tried to fix it, but didn't succeed. And even worse, these are all classified as 0, even though there is nothing there. So few books. These are very easily accessible books, I would say. An Introduction to Statistical Learning, more applied predictive modeling. Both of them teaches you, gives you a good starting point for starting to do predictive modeling and feature extraction. The other thing I recommend, and then we're going to start that during the hands-on session, you really need to learn how to program. There's no way around it. So this is a good starting point. R is, since you now all have RStudio installed, you should go home and continue using it. And there is a PDF available of this book online. So I think all of these books are available as PDFs online also. So I hope you've learned a little bit about how to train predictive models and then how to test them to avoid overfitting.
Hi David, I have a more general question. So you gave us an example of this 1940s presidential election, Truman result. So we have come a long way, right, 2018, but we still seem to be getting this thing wrong time and time again.
Yes, 2016 was another example.
That was a good example, and right now I'm going in, it's election season in India as well. So I'm sure we'll get it wrong, or many of the outlets will get it wrong. So what's your take on that? Why are we getting it still, so wrong?
I mean, I'm not, don't know that much about predicting elections, but in general, in let's say biomarker discovery, or I mean, we get it wrong for one thing is that we don't think about it maybe well enough. And we take shortcuts. But it's also very difficult to do it right. That's the main thing, I think.
Number of variables there?
Yeah, and also, I mean, it's not easy to collect enough samples, so we have to do them over many hospitals, and it gets very complicated. And it's actually, it is not easy to think it through.
So you mentioned that the normal tissues in cancer situations, the normal tissues will not be collected from a hospital which is remote from the ones where the cancer tissues are collected. So one is there could be ethical issues here. Like if you want to collect it from the same hospital, there could be ethical issues. And the other is such a scenario is generally not seen, where the normal tissue and the cancer tissue both are removed at the same place. So there could be another institute where for other reasons similar type of operations are being held, and for which not really cancerous but other disease tissues which we could consider as normal or not cancerous, let's say, not really normal but not cancerous also could be used. So in that kind of scenario, how would we
I mean, Mani talked about some solutions like trying to do batch correction and things like that, but again, it's, as I said, better to avoid that if possible. So one should definitely try to have that, let's say, normal cancer patients are, I mean, for example, for blood testing, one could imagine that there is a clinic where people come, and when they come there, they don't even know if they have cancer. The doctors don't know. So that's a good situation that during the testing, no one knows, and they are treated the same way. And only after the samples are taken and have been tested. If one can do that, that's the ideal situation, I think. But usually, I mean, often we do have to make compromises, but we should try to make as few compromises as possible.
So I have two comments to make. The political thing that you brought up is a lot more complicated because human psychology and how people behave is involved. I think the example David gave was for showing bias, but the one you brought up about the 2016 election is a lot more complicated. So who goes to elect, or who goes to vote is also part of the prediction, and so the polling does not take that into account in a proper way. So I hate Hillary Clinton, so I get all my friends to come and vote for Trump. So that dynamic is not taken into account when the polling is done. So I think that's a much more complex example that involves human behavior and psychology. So I think that's off the charts for this course. The other comment I wanted to make was David brought up feature selection, and he also talked about keeping your test data set separate and using cross-validation. So one of the common mistakes that people make, and one of the mistakes I made too early on, is to use your entire data set to do feature selection and then split your training test set.
Yes.
So that is a very bad, so if you're working in the business world and you have millions of data points, I think it doesn't make that big of a difference. But in biology, where you have only 100 or 50 samples, if you do that, then you already have your answers in your features. And so you will do very well on your test set, but the next set of new samples that come from the hospital, you will fail badly. So I used to work previously in the telephone industry, where you get hundreds of thousands of samples or records. But when I moved to working on biological samples, you really have to pay attention to not contaminating your training and test set and keep them separate from the beginning.
My question is that, see, I developed a kernel or trained my kernel on set of features selected from a large number of features and selected small number of features on which my model is already developed. Now when I go for testing, the test data set somehow misses one feature, that feature is NA, that could not be collected from the population sample. In such scenario, what is the way out? Again, to go back and develop the kernel with one less feature, or can I, is there some way out to manage the same train model?
So some machine learning methods are better at handling missing data like that. So especially some of the tree-based methods, there you can set them up so that they can, even if you have in your training set a feature and then in the test set it can still work well.
Like random forest?
So when in tree-based methods that David mentioned, especially the random forest, when you build your model, you can turn on storing surrogate features. And so when your main feature is missing, you will use your surrogate feature instead of that. And so if you have like 5 surrogates for each main feature, then if 1 or 2 of your main features are missing, you can use the surrogates. So obviously there is some degradation in the model, because if the surrogate was as good or better than the main feature, that would have been the main feature. So you will lose some performance, but you can still do your prediction.
Is it the same thing that interpolation and fixing some more data points?
No, that is missing value imputation. That is different. I spoke about it day before yesterday, but that's another thing you can do. But I think using surrogates is a more robust way of dealing with it, because when you impute, it's one thing to look at all your data and impute, but when you have test data, which is just a few samples, how do you impute? Do you use only the test data to impute, or do you use your entire training data and test data to impute? So I wouldn't recommend combining everything to impute, because then you're kind of making your test data look like your training data by design. And that's not what we want. And so the ideal way would be, if you have a large test data set, you can try imputing, but usually we get a few samples for prediction. And in that case, I think using a method that can deal with surrogates or missing features would be the best approach. I know only random forests that can do that. I think for some of the others, you can calculate variable importance, but I don't know some other methods that would use surrogates automatically. Maybe
Yeah.
David knows others.
Yeah.
So, today Dr. Fenio provided a brief idea about different biomarker selection methods and how it could help in optimal selection of features. We also learned that cross validation, forward selection and backward selection plays an important role in feature selection. LASSO is a very good software to explore these kind of extraction features. We should choose features keeping in mind two important things. Models should be as simple as possible so that we could interpret easily. At the same time, the model should also provide a good prediction. Today we also learned curse of dimensionality. In simple words, the complex algorithm and data frame having a big number of dimensions or features frequently make the target function very complex, and it may lead to the model overfitting. Finally, Dr. Fenio talked about sampling biasness and biomarker discovery. He also mentioned about data snooping. It refers to the statistical inference that the researcher decides to perform after looking at the data. We should avoid sampling biasness and construct pre-planned interferences. For example, a group of researchers plan to compare 3 dosages of a drug in clinical trial. They pre-planned the data comparison on the basis of record of patients and group the patients on the basis of that, which is an example of data snooping. The next lecture will be a hands-on session on Web Gestalt by Dr. Bing Zhang. Thank you.